Good afternoon and welcome to the IMSC Diamond Jubilee lecture series. Today we have a very distinguished speaker, Professor Govindarajan, who will be speaking on geometry beyond Riemann and gravity beyond Einstein. So Professor Govindarajan and I have had an overlap of more than 30 years almost in this institute. So for the older people here, he doesn't need any introduction. For the students, my name is Murthy, and we have been colleagues, as I said, for a long time. Professor Govindarajan did his studies in Madras University. He got his master's and PhD from Madras University. Worked with Professor Matthews, and then he joined the institute somewhere around 1991, and since then he has been here. He has worked in various fields actually. I remember in the beginning when he joined, he was working on string theory actually, and then knot theory, and he has worked in high energy physics, he has worked in gravitational theory and mathematical physics. So a variety of things he has done, and he's also one who has been passionately involved in popularization of science. He's been part of Tamil Nadu Science Forum since its inception. I think he's one of the founding members of this organization. And since that time, he has taken a lot of interest in not only giving lectures, but in organizing various events involving children and students in secondary schools and undergraduate colleges, etc., etc. So a variety of things that he has done over his long career, and it's still going on, and we should expect more and more things to come from Govindarajan. So please.
Hello, can you hear me? Okay, thank you very much for interesting introduction. Since he mentioned about popularizing, in fact, I'm going to give a talk tomorrow to Tamil Nadu Science Forum on Hiroshima Day. Tomorrow is Hiroshima Day. So I'm giving a talk there also. And that will be mixed with Tamil and English. So, and it will be available on YouTube also. If any of you interested, can take it up. And also he said distinguished, and I remember one of the former directors of this institute introduced a well-known person. A.P. Venkateswaran was his name. He was the external affairs minister, and Rajiv Gandhi was the prime minister at that time. And then of course he was called for this institute, and George Sudarshan had to introduce him. And unfortunately, by the time he came, he was dismissed because he made some remark. And George Sudarshan, true to his color, he introduced the speaker as A.P. Venkateswaran is a distinguished external affairs minister, now distinguished external affairs minister. So that's the kind of a thing. I hope I'm not that. Anyhow, so I hope to make this talk. Thank you very much. Thank you. So I hope to make this talk. I anticipate a lot of students are there, and of course, maths and computer science people have also come. So I've tried to make it as a uniform. Everyone will appreciate or understand everything to the best of my knowledge, to the best of my abilities. So this is the thing. geometry beyond Riemann and gravity beyond Einstein. So in order to tell this, I should tell what is Riemann's contribution to geometry and what is Einstein's contribution to gravity first. That will be initial part, and then why we should go beyond that. And very interestingly, both Riemann and Einstein have themselves made a remark that they have to go beyond, the real thing, geometry has to go beyond that in both the ways. And that is what is interesting, and I hope I will be able to drive that message. Okay. So this is going to be the plan of my talk, Riemann and his geometry, which is essentially non-Euclidean geometry. Okay. Now we know, we take it very lightly, easily, but if you put yourself at the time when he was there, even the talk of non-Euclidean geometry itself was kind of a taboo, and I'll tell you why. Then I will briefly mention something about the other forces, because this non-Euclidean geometry was used by Einstein for his gravitational theory, but there were other forces which people could do a lot of experiments, etc. I will mention something about it. Then I will talk, next one will be about beyond Riemann and Einstein, and then something about geometry at the infinitesimal. These questions were posed incidentally by Riemann himself, very interestingly, those questions, and he left it unanswered in his talk. So that's my scheme of thing. So this is the starting point. Bernard Riemann gave his habilitation talk on axioms of geometry in 1855 in front of Gauss. Of course, before that, Euclid, several centuries before. And people did a lot of work in Euclidean geometry, 2 dimensions and even 3 dimensions. And what they knew in our language is R3, real three-dimensional space. That's what they knew. And probably they can put a sphere. They can consider Earth, they can consider orange, whatever you want, they can do that, and that's what they knew. So Gauss did develop these 2-dimensional surfaces very well and introduced the ideas of curvature, etc. within his framework, which is a curved geometry. You can call it curved geometry in low dimensions, which is essentially 1 and 2, circle or many circles you can draw. And geometry you can have in 2 dimensions like a sphere or something like a donut and various other things you can imagine. That's what you can do. But what about 3 dimensions in which we live? Is it also curved? How do I know this is not curved, etc.? How do I understand that? So that was the question Gauss was interested at that time in 1855, around that time. And this talk, habilitation talk in German, this thing is in Göttingen University. If somebody wants to become a professor, unlike our times now, they have to give a talk to distinguished people who will come, and it has to be profound, and he has to reach all the people. And they choose, the person chooses, Riemann, having done good work, chooses 3 topics, 1, 2, 3. Okay, and usually the person, the head of the supervisor, whoever is checking, head of the selection committee if you want, they choose one of them, and being considerate, they will choose the first topic, assuming that must have been his first choice, that person's first choice. Unfortunately for Riemann, which essentially he was prepared, Gauss chose the 3rd topic. And that topic is about the axioms of geometry. Axioms of geometry. That is the thing. And this is the question. So he took it. And I'll tell you what is there. Only the genius of Riemann broke through to a new conception of space. This is 3-dimensional space, or even higher dimension if you want, in which it was deprived of its rigidity. So is there a rigid thing between everything is same here, etc., etc., or is there anything, something like, imagine if you want, if you're inside a swimming pool or somewhere, you want to go to one place to another inside the 3-dimensional box of that type, you may find it difficult to go in one direction or another direction. Okay? So that will be, you can put it on geometry if you want. So that is a kind of a, if there is no rigidity, then R3, there is only Euclidean space, nothing is, it's a vacuum, space is, nothing is there in between, and the distance is what Pythagoras gave, x1 square plus x2 square plus x3 square, or x square plus y square plus z square is your distance, or dx square plus dy square plus dz square. So that's what, now if I tell Pythagoras, it might be controversial. Now probably I should include something Sulba Sutra or something like that, but let us take it as Pythagoras' contribution. Club, small club, some 4 or 5 people who were interested, and then that club is called Olympia Academy. And then they discuss papers of Riemann, Hermann von Helmholtz, Clifford, Poincaré, and others in their cafes. They'll go to the coffee place, discuss various things of this kind, focusing on non-Euclidean geometries. So this is the paper. This is the talk, actual talk he gave on the hypotheses which lie at the basis of geometry by Bernard Riemann, and it is in German, so it has been translated by Clifford much later, and several other people also have translated. I have taken this translation. Okay, so this is a thing. So what does it say? To talk about non-Euclidean geometry in those days was a taboo because they didn't want it. R3 is R3, there's nothing there. You don't find any problem to go from, in 3 dimensions, to go from one place to another place, everything is equal. And following Kantian philosophy, philosophically, all non-Euclidean geometries are nonsense. This is what effectively they were trying to make. And before the 2 dimensions, our own Gauss has given various things about how the curvature can make a difference, that to go from one place to another place, etc. So Riemann, in his talk, he never mentioned non-Euclidean geometry in his whole thing. He didn't even, probably he was so hesitant to even utter that word. But he essentially generalized Gauss's theory of curved spaces to higher dimensions. How do you give it? That's a point. Okay. So what is the generalization of curvature, etc., etc. So in the whole talk, there is only one equation. Unlike other mathematical talks, there is only one equation, and that equation is essentially this thing. ds is equal to square root of, or you can say ds square is gij dxi dxj. So to go from one point to another point along a curve, you make this kind of a thing, and if you go along the curve for longer distance, probably you would have to do bit by bit, okay, bit by bit, and add all of them, you will get the total length. He used the idea that in an infinitesimal neighborhood, you go to a point in that 3-dimensional space, any higher dimensional space, in that point, it's almost a plane, or almost Euclidean. Even a curved manifold is flat, tangent plane in the modern sense of the term. And to appreciate his motivations and development of the axioms, we have to go back to physics. And that's surprising for me, because when I started looking at this thing, I never realized to give this talk he was motivated by physics. And of course his mentor, Gauss, okay, himself was a very well equipped in his physics, and he has done several pieces of work in electromagnetic theory, mathematical parts of electromagnetic theory. Gauss was an expert in surveying as well as astronomy. He was director of Göttingen Observatory itself. So he had a lot of interest in physics. Riemann himself, very interestingly, was involved in the measurement of velocity of light by measuring the charge in Leyden jar. This is one experiment people have to do, they were doing, and he was interested in that. Can I find it? Before that, there were other experiments, astronomical experiments which were there, but in lab experiments, and he was interested in that. He came to the insight that electromagnetic potentials, so you have the potentials which is due to a charge or a moving current, okay, moving charges, propagate through empty space at the speed of light. In fact, he has mentioned it in one of his diaries which is now published, he has mentioned it. This was around the same time as Maxwell, to whom we credit this work completely, which is true, correct also. Published work is only by Maxwell, inspired by Faraday's intuitions. Faraday did all the experimental work. From there, he went to this kind of a thing, and this is a thing. In Riemann's vision, what he wanted was this electromagnetic potentials, electric field and magnetic field, what you call nowadays electric and magnetic field. Supposing you have a charge here, another charge here, how do these two things interact? How does this charge affect that charge? That's a question. So we will say there is some electric field. That electric thing propagates, okay, through and affects the other one. This is the common sense in which we say, like even Earth and Sun, there is some gravitational field that affects it, because we don't want action at a distance. So this is a kind of a thing. So what he had was, supposing I speak here, you are able to hear, because there is a medium here, and the pressure differences, etc., propagate and reach you. Like that, there is internal pressure in this ethereal medium, in which the electric charge is there, it propagates and go to the other one. Okay, so he needed a medium to carry this information, that there is a charge here, etc. And earlier they used to call it ether. Okay, they used to call it ether. And you can call it the field. What he imagined was the field. Okay, the field is there in between, anywhere. There is a charge here, there is a charge, and due to this charge there is a field everywhere, which he called as an ethereal medium. Riemann proposed a theory of electricity along with Gauss and Weber, that electricity cannot propagate instantaneously. That's the first point, but only with a speed, like our velocity of sound, like that, there is a speed, because he associated with a wave. If you have a wave, there is a velocity for that, speed with which it goes, like water wave, etc. And he wanted a finite speed for that, so it cannot be instantaneous. And that is the only thing. He even mentioned electric phenomena travel with the velocity of light. It's very interesting. He has done. We always associate this with Maxwell, but in his diaries these things were there. Very interesting. Riemann's lecture appeared in print after his death, 10 years later. There is another person close to around that time, Helmholtz, went further. Space may not be rigid. The space which you have between one charge and another charge, R3, it may not be rigid, like fixed everything. It may have curvatures in between, and that curvature may be even changing. What the curvature here may not be the same as here, and may not be the same here. Okay, so that is also possible. They even wanted ether with physical properties like elasticity. So this medium is there in between, and that has physical properties like elastic properties. Like it can stretch it, you can compress it, you can do anything you like with that. That is the kind of a thing they wanted. Okay. So this is Riemann's Nachlass, is essentially private diary. Makes hypothesis where all these statements are there through his involvement in electromagnetism, physics. Universe is filled with a substance that constantly flows into the atoms. One atom is there, another atom is there, where it disappears. Once it reaches that other charge, it disappears. He probably had the notion of fields and atom as the source of ether, okay, or ether, source. There is atom which is a source. In between, that field is traveling like a wave. And that medium in between, you can call it field, or they call it ether at that time. It is possible to express the force of universal gravitation on atoms in terms of the pressure. So like Earth and Sun, you can express it by, if there is some ether, there is some pressure difference, and the pressure is communicated to Earth from this thing. That also travels with some velocity. It's possible, and to think of force of gravity as being dependent on this. It follows that the space-filling substance must propagate the waves that we perceive as light and heat. The real motion of the substance in empty space must be assumed for the explanation of gravitation, and the motion that must be assumed for the explanation of light. These are all his statements in the diary. These two phenomena, gravitation and light traveling through empty space, must be the same, anticipating the speed of gravity. This is the most important thing. The last 10 years, there is some actual experimental evidence, the speed of gravity is same as speed of light. Okay, that is the point which is coming from the current gravitational waves experiment. Okay, this actually, he actually makes a remark about it in that place. Okay, the next set of people, based on Riemann, Clifford suggested space in small parts are like hills. Small parts are like hills. But on the average it is flat. On the average it is flat. And this variation is what happens when we arrive as matter in motion. So there is matter where there is some extra and hill which is there. But he didn't say what is the scale of that smallness in his thing. There is one more person, Newcomb. He was actually doing astronomical things. He was looking at the perihelion of Mercury. So he took that Mercury goes around the sun, but not come back after one revolution, but slightly shifted. Why is it shifted? Well, there is Jupiter, there are other planets. So he accommodated all of them, but still found by his calculation that there is some extra. That extra was 42 seconds of an arc per century. That is the extra. In fact, Einstein himself acknowledges that. And that kind of a thing was acknowledged by Poincare himself, which is very interesting. And he said that can be obtained by an extra force. Poincare mentions that extra 42 seconds can be obtained by an extra force. This is what he mentioned. So Einstein's Olympia Academy spent a lot of time in discussing Poincare's science and hypothesis, which kept him breathless, according to one of them. Poincare even discussed the question of bending of light. So now I have started talking about the space R3. The space is no longer flat. It is curved by itself. It is internally, curvature is there. Now if there is internally curvature, to go from one point to another point, we should look for what is the shortest distance. If there are curvature, then the shortest distance may not be a straight line. So you have to bend, you have to go along some curve. So Poincare assumed this R3, the thing, the non-Euclidean geometry, even in 3 dimensions, is curved, because of which the straight lines are not the things, so there is a curve. So using that geodesic, what we call as geodesic in modern terms, even the light will only travel along that. So even light will be bending. Even light will bend. Earlier people were assuming light will not bend. But now even this assumption will bring in, and he even calculated some of those things. So Poincare even discussed the question of bending of light and remarks somehow Euclidean geometry. In his writing, he said, no, I somehow prefer Euclidean geometry. Whenever there is a bending or some of the curvature changes taking place, I will introduce extra force. I will introduce extra force so that is what is bringing you to the changes the direction, etc. And additional forces to cause the bending. In fact, Einstein was very worried about this thing. He pondered for a long time. Poincare is on the foundations of geometry. This is the work. Elaborated earlier ideas and concluded space is to be defined by a group, right? This is what people earlier used to call it as a Erlangen program, that you define by, you don't say this thing, it is by rotations which leave the space invariant, which does not. So you talk about rotations. That's what is used by Poincare as his definition. Okay, but Einstein, now comes Einstein. So what happened is 1905. There is a famous year, Annus Mirabilis. Essentially, he introduced the space and time, okay, the velocity of light, which was worked out by Maxwell's equations, etc. And later, Millikan's experiment indicated that there is no ether. The velocity of light is the same in all, whether you are going in a train, whether you are stationary or any other thing, velocity of light is the same. That's a kind of experiment. So they wanted Minkowski space-time, which is space and time are not separate, they are one and the same together. So observers from different inertial frames, they call it inertial frames, okay, will observe differences, but the invariant quantities will agree. This is actually what is called Euclidean geometry, but with a slight twist, which is called pseudo-Euclidean geometry. What is there is x1 square plus x2 square plus x3 square minus c square t square. There is a minus sign which is introduced between space and time. That's why people call it as a pseudo-Euclidean geometry. That is the name for it. The determinant of the metric is -1. If you want to say that as a matrix, that is what will happen. This was needed to understand Maxwell's equations. Maxwell's equations were experimentally and everywhere everything was verified, which is also true with light, optics phenomena. And the important thing is that space, which was Minkowski space, is flat within quotes, and there is no need for ether. There is no need for ether. Ether was made irrelevant, okay, by Einstein in 1905. That's what that famous paper indicated. Now, Einstein went beyond this in the next decade. That is 1915, 100 years before. Sorry, I should have corrected it. The general theory of relativity. And there is a lot of discussion about the mathematics people like Hilbert, etc. They were also attempting, because of this connections to the curvature, etc., Riemannian geometry. And Einstein also, who was motivated by physics and various other things, along with his friends' help. I will not talk about them. Basically what happened was Einstein introduced the symmetric matrix Gij, which I wrote, and using that Gij he came to this famous equation, which is called the Einstein's equation, where don't bother about this thing. This essentially incorporates your curvature of the space-time. Now the curvature of the space-time is indicated by what is called Riemann tensor, and then R mu nu Ricci tensor, and then scalar curvature R. All those things are tensorial calculus. So the equation on the left-hand side talks about how the geometry is. Everything is given by the geometry of the space-time. The equation, the term on the right-hand side, T mu nu, is energy momentum or tensor, or what you call as a. This is the kind of equation, in fact, Newton kind of people earlier wrote, which is del square phi is equal to rho. That's what people will write. If there is matter here, the space is producing a potential like that. So you have like sun, earth, etc., which is giving you the T mu nu, and the left-hand side gives you the space-time, which is curved. That's what is happening. So essentially matter, which is energy momentum tensor, curves the space-time, and the curvature determines the path of the particles in the space-time. So sun curves the space-time around it, and the earth, which is moving in it, is taking an elliptical orbit. Whatever orbit you want to have is the thing. So this is a mutual arrangement between them. No doubt Einstein theory is very beautiful, because it is geometry. Completely everything is geometry. Also, it has tremendous success to understand gravity in solar scales, solar system. All the things, everything fell apart. Now, as I told you, perihelion of Mercury was one of the greatest things which was recognized by Einstein himself, which brought that 42 seconds of an arc exactly. That's what made that whole thing people became. And bending of light was experimentally measured by Eddington in 1919 by looking at the solar eclipse, because during the solar eclipse, the whole thing is dark to some extent, and there is a star becomes visible even during the daytime, and how that light from there is bent. That's what he calculated, and it agreed. This is the basic thing. Now, the general relativity is so successful. Now your cell phones which use GPS, etc., makes those corrections. The time here and time in US, time in New York or Paris or anything, they have to be corrected according to these things, and they use it. And even the CERN machine, where protons go around in 27 kilometers, this thing, and they go at tremendous speed, close to that of light. So they have to make corrections due to general relativity. Not only special relativity, even general relativity corrections have to be incorporated. So this is an important thing. Now combined with nuclear physics, my friends will tell me, proved very useful in stellar structures, sun, etc., various stars. And the fate of stars like sun to become white dwarf is well understood, Chandrasekhar limit. But only thing is, parallelly something else was happening from 1900 to 1930s when these things were there, and that was quantum theory, where hydrogen atom spectrum, various things were there, and such a thing was parallelly happening. Now you have one force which is electromagnetic force which was understood on the matter side, another force which is gravitation, and later three more forces were there, weak strong interactions were also included. So there are four forces. Why are they four? What is happening, etc., are big questions around that time. To appreciate Einstein's thinking, we have to go to his original papers post 1915. I have written it correctly this time. The popular exposition by himself, he himself has written a book called Special and General Theory of Relativity, and Geometry and Experience, The Problem of Space, Ether and the Field in Physics. These are all books which he had written post 1915. In Geometry and Experience, he goes into the philosophical questions. I told you about Riemann and others, that is there something in between? Is there matter? Is there ethereal medium in between, etc.? With the contention that axioms of geometry are creations of humans, this is his profound statement, we will not worry about it. He credits Riemann and Helmholtz and confronts Poincaré's contention that choice between Euclidean and non-Euclidean is only a convention. That was Poincaré's contention. What is that? Okay, I prefer only Euclidean. Whenever there is a change which is happening due to what you call as curvature, I will introduce extra forces. That's all. This is what Poincaré said. He goes on to say, very interestingly, I have to use some Latin things, subspecie aeternatis, which essentially means to the eternity, to the grace of God. Okay? Poincaré is right. He says that. He says Poincaré is right. But we must proceed along non-Euclidean geometry because it underscores universality of gravity through geometry. Okay, I don't have to find out what is the force, what is this thing every time. Okay, there is some universal law I create, like Newton created a universal law of gravitation. Like that, universal law of gravity is given by the curvature. So in his non-Euclidean geometry and physics, he credits Helmholtz and says that without him this formulation would have been impossible. Okay, so this is so far as I will come back to this thing after introducing a little bit of quantum mechanics, little bit. So this is about gravity and other things. Success of quantum theory is reflected in constructing an unified model for describing electromagnetic and weak interactions later. For this, first I have to go through special relativity and quantum mechanics through Dirac equation. I'm not even talking about Schrodinger equation. So this is that equation which is there, which essentially people will say in physics, I d slash minus m acting on psi, or gamma mu d mu. Gamma mu is a matrix and d mu is a partial derivative, minus m psi. This is the Dirac equation. And if you want electromagnetic interactions, you correct the derivative d mu by minus IE a mu, vector potential which is there. That a mu will have four terms, a naught and a1, a2, a3. The vector part of it will give you magnetic field, and the scalar part will give you the fourth component will give you the electric field. That's basically the idea. The important thing is that gamma mu are matrices of Clifford algebra. What he did was, the way Dirac was actually playing a simple trick, if you want. He took something like del square equation, took the square root of that. But square root he wanted as a invariant quantity, so that's why he put gamma dot d. Okay? So he took the square root of that, and that's what he had done. And this is that equation, gamma nu is 2 times eta mu nu, which is as eta mu nu is nothing but a simple matrix, 1, 1, 1, minus 1. That's all. What I gave you, x1 square plus x2 square plus x3 square minus c square t square. That is what is the thing. Now this is for the Minkowski space. If you are in a curved space, then the eta mu nu is no longer eta mu nu, but it becomes g mu nu or gij, which I said, which can depend on position. So that can change to 2g mu nu. That is my equation number 5. This is what is the non-Euclidean thing. Now a very, very basic one-page introduction to what happens to the rest of them. The standard model uses what is called the gauge group, SU3 cross SU2 cross U1. Don't bother about any of these things. And it also has W bosons which are massive, because weak interactions don't travel from one end of the world to other end. So it's short term. So they wanted that particle which carries that information to be short, they are massive, they don't go far beyond some distance, and that is the reason for this thing. The above model was proposed in 1970s when I became a graduate student, around later part, in fact just before I becoming graduate student. I was a master's student or undergraduate student, and till now it has been completely successful. In fact, there are no evidence except for minor things that there could be something we have to look beyond. That's what has happened so far. Several attempts, of course, people want to go beyond that, theoretically, so that you can try to say something, but so far experiments have not forced anything beyond that except minor small things it's here. So that is as far as standard model is concerned. Now this thing also helped to understand what is known as the Big Bang theory of universe. So 14 billion years ago there was a Big Bang, and the expansion of the universe started, which was obtained by Hubble. Okay? So the distant galaxies go faster and faster. The farther the distance, farther the speed is also higher. That you can find by redshift. That's what they did. So now we know, based on all these things, in addition to solar system, which was known only earlier, before around the time of Galileo and others, they knew the stars which are visible, but about galaxies, etc., became known. Now we know that luminous matter constitutes only 5%. There is 24% of dark matter, what we call dark matter. I'll tell you the reason for that. And the rest are dark energy, which is responsible for the acceleration of the universe expansion. Expansion is there, and that acceleration is there. So these are the three factors. The matter which is there in the universe, these are the parts which are there. So Einstein tried to unify electromagnetism and gravity and did not succeed. That was one of his, till his death, that was one of his ambition, and he didn't succeed. But the fact that there are two structures in space, one is electromagnetism and another thing, both are geometrical, and they are not together, is intolerable for him. So there was attempt to bring gravity and electromagnetism together by going to, instead of 4 dimensions, why not 5 dimensions? So make the 5th dimension a small circle. So that circle is so small you will perceive only 4 dimensions. This is the assumption which people made, which are called Kaluza-Klein theories. Now, if you can go up to 5, you can go even more. So now modern people talk about 10 dimensions, 11 dimensions, 26 dimensions, etc., etc., to unify all the forces together. Now, honest remark which I have written here is, there is all these attempts have not been reasonably successful to say that we can take it for granted. Because all the supersymmetry, supergravity, superstring theory, etc., on which, as Murthy said, I have also dabbled in. And so far I would honestly say your standard model works very well. There is no clue to go beyond this except for minor tinkering here and there. So now the extra dimensions were taken to be 10 to the power minus 33 centimeters, okay, which is nothing but Planck length. So I have to probably go a little faster. So that Planck length is what I've written with fundamental constants. So this is basically the idea. Now beyond Riemann, so far what Riemann and thing, now I have to tell about what is beyond Riemann and what is beyond Einstein. At the galactic scale, beyond the solar system, as I told you, there is dark matter. How do I know? Now if you take the central part where there is a huge supermassive black hole, and then there are stars very close to that, and there are stars far away from that. Now it is almost like our solar system. We know that faraway planets go slower and slower. Okay, faraway planets go slower and slower. That is Kepler's laws. So you expect the same thing. They all go around the solar thing, etc. And you expect the faraway stars will go slower and slower. The velocity curve, what is called rotation curve. Okay, and that curve you expect is A. The curve A is what you expect. The velocities as a function of distance from the center. But unfortunately it is not that. It is B. It is no longer going on this thing. So what is it you can say? Okay, if that is the case, there is matter in between. There is there is some matter which is there in between which does only gravitational interaction, which makes sure that B curve is followed but not the A curve. This is what is responsible for what you call as a dark matter. First we have to make sure those dark matter things do not do any of this luminous. You don't see it. There is no light. There is nothing coming of that type. So you have to make sure that they don't do that. That interaction is not there. So this is because all other stars are only seeing by electromagnetism or X-rays or whatever it is you have, radio waves, etc. So this is basically the problem. So this is the curve between A and B is what was bothering people. So various things are there. I will not talk about all this. Galaxy clusters, mass distributions can be measured. So there are several solutions. So let's take the bullet number 4. At the several candidates like SUSY, supersymmetric candidates, there are extra particles there. And Higgs, sterile neutrinos, our own institute people, a lot of people are actually in our institute, they are doing good work on these things. So there is one new thing which I have also been involved, which is called fuzzy cold dark bosons. Okay, I will tell you what this thing, very beautiful. The fuzzy dark matter is a model which suggests that dark matter is composed of ultra-light particles, very, very light particles. Well, these people are worried about the mass of the neutrino, which is maybe 0.1 electron volt or 0.01 electron volt, but the particles which suggested are 10 to the power minus 20 electron volt. Okay, so that is the thing, and that we called it as Stickelberg field. And with a student from CMI, I did the work, and that student has gone, help from this thing is he got perimeter admission. Okay. So there are other people who talk about modified gravity. Oh, we have to modify. If you don't modify geometry, you modify the gravity, right? Beyond Riemann or beyond this thing. So people say modified gravity, which is called modified Newtonian gravity or thing. For dark matter. But only thing is, if you are going to modify like that, the beauty of geometry and other things are completely lost. That was what was bothering many people. So now we have to go back to understand this, where these things anticipated the master himself, that is Riemann. So you go back to that same paper which I mentioned, and he actually talks about some of these issues. He has given the axioms, and he was worried about whether those axioms are correct at very, very large scales, infinite extent, or is it correct at infinitesimal scales. Very, very small scales and very, very large scales, are these axioms correct or not? That is the question he himself has posted there. The axioms may need changes at infinitely, by infinitely, he says infinitely, I would take it as very, very large distance, like galactic scales, because the scale which was known to Riemann was only solar system. So that is only the kind of thing he was aware of. Or he doesn't know about atoms, inside atoms, so that is also infinitesimal scales. So this is about the fuzzy dark matter. This is actually flicked from one of my early other talks, so that's why the red colors have suddenly appeared. So we have proposed particles of the mass 10 to the power minus 22 electron volt. Now the problem with these particles of this type is they are very so light, they will travel always with the velocity of light, what you call as velocity of light, 3 lakh kilometers. So when the origin of the universe is there, the expansion is taking place, they will go very fast and completely decouple. They are relativistic. That's why all these people who are looking for dark matter of high mass, they look for non-relativistic particles. So that is what is the problem there. They will travel very close to the velocity of light and decouple very early, and that will not help. That is where Bose and Einstein help, interestingly. Remember Bose's paper through Einstein, and Bose-Einstein condensate is one thing. That is the Bose particles, they try to stick together and forming, even if they are very, very this thing. So how does it help? Don't bother about all these first things which are taken there. Only thing is, if the Bose particles below a particular critical temperature, they try to stick together, forming what is called Bose-Einstein condensate as a blob, even though the tendency is to fly apart, even though their tendency is to fly apart. And that formula 6 tells you what is that mass. It is a function of that mass or the particles, gas particles, like what we learnt in our college days, kinetic theory of gases. That is what the critical temperature is. Okay, is it found experimentally? Experimentally, Bose-Einstein condensate has been discovered, and the temperature at which it has been discovered was nanokelvin. You have to go to minus 273 degrees centigrade, or very close to that. Nanokelvin is the expected temperature. Okay, but the gas which is molecules which were there was rubidium, which is very, very heavy, 86 GeV. Just compare 10 to the power minus 22 along with 86 into 10 power 9 eV. So that's the kind of a difference. So critical temperature was nanokelvin for those things. Now I can ask the question, what is the critical temperature for these gas particles? And it turns out to be, it is very close to Big Bang temperature, 10 power 19 degrees centigrade. So if they are formed at the time of the universe starting, later, let us say, when I say time, it's not 1 second or 2 seconds, it may be about 1 million year, 100 million years, that kind of a thing. That's what Webb thing kind of thing is talking about, 300 million years later than Big Bang. So there will be, if that blob is there, that blob will be a fluid, gas, like a superfluid it will be there. It will not do anything because there is no, the condensate will allow, if something is going through that, it will simply allow. So it will transmit, no problem. Okay, so this is what is the thing. So now I'm going to change the gear. The gear is the ether, which was talked about by Riemann and also later others also, which was dropped by special theory of relativity. But the same Einstein, in a paper in 1922, he says to deny ether is ultimately to assume that empty space has no physical qualities whatsoever. The fundamental facts of mechanics do not harmonize with this. He said, we may say, according to general relativity, space is endowed with physical quantity, like elasticity. Space is endowed with elastic properties. We don't feel it, but for that you have to go to different scales, like galactic scale, etc. At that sense, it is, the elasticity is so very little that you don't feel it because of the fact that it is superfluid. There exists an ether. According to general theory of relativity, space without ether is unthinkable. This is Einstein himself. For in such a space, there would not be no propagation of light, but also no possibility of existence of space and time. So you should not assume it is a regular matter which we know. It has to be new kind of matter, like the Bose-Einstein condensate. Okay, different type. That is what he says. Okay. Now it is not only Einstein. In 1951, Dirac, I always look for authorities. So this is one more authority. He has a paper in Nature called, Is There an Ether? He answered, we can now see that we may very well have an ether subject to quantum mechanics. Because what is ether is, you are talking about vacuum. Is vacuum where there is no particle which is there, is quantum mechanical is not valid. The particles are created and annihilated all the time. It is always foamy. Okay? That quantum mechanical vacuum is not like a classical vacuum, nothing is there. So this is the basic idea. So not titanable in practice, and this is the kind of vacuum, and that is needed, is what Dirac himself has written in 1951. Of course, there are other experts like John Bell, from where Bell's inequalities, etc. have come, and Laughlin. All these people have unfortunately got their Nobel Prize and died. Laughlin is still alive. Sorry, Bell is alive. Okay, so this is the thing. So that is not the only one, and we have a very close connection, and that connection is here. So you expect that fluid which is there everywhere in the universe with different densities in different places, okay, we will feel that there is some problem. So it will affect the motion of Earth and other things through that. So this was one of the questions people were worried about, and this gentleman who was the director of this institute about 30 years back, in 1976, around the time when I became graduate student, he wrote, and we used to essentially laugh at that paper because of this suggestion, ether, because we all assumed ether is not there. But he also was bold enough to say this, a new model for ether as superfluid of fermion antifermion pairs described a macroscopic wave function like the condensate fluid, superfluid, pervading the entire universe and may account for missing matter. This is what he has, this paper, this is, they even didn't know what is a possible thing. So this is the idea. So this is as far as the long distance, which is posed by Riemann himself, large distance. Has he made any remark about short distance? What happens at very close distance? Should you change geometry at close distance, short distance? When I say short distance, it is very small, 10 power minus 30 centimeters, very small. Okay? Riemann says that at short distances, now it seems that the empirical notions on which the metric determinations of space are based, the concept of solid body and that of light ray, lose their validity in the infinitely small. It is therefore quite definitely conceivable that the metric relations of space in the infinitely small do not conform to the hypothesis which he himself has generated. That first part of the paper, these things may need modifications. Why? Because at length scales, small scales, we need, supposing there is a particle of zero size, zero thing, inside a small box of 10 to the power minus 30 centimeters. If you want to see whether it is there, what is the distance up to which it is thing, you have to send a gamma ray of that wavelength in order to observe it. Now that kind of a gamma ray which you send will have energy, and that kind of energy will create a black hole of that size. That is the size for which it will happen. So if it is a black hole, you don't know what is happening inside. That's what general relativity tells you. So the famous Heisenberg's microscope experiment is repeated for space itself and says that you cannot measure it within this thing. So this is another way of saying I cannot measure any distance less than 10 to the power minus 33 centimeters. That is the lowest I can measure. So what was required is, this will interfere in measuring things. So we need new geometry, axioms of geometry to include quantum space-time, because now I am bringing in quantum space-time, quantum nature of particles, etc. And that geometry, people have called it by the term non-commutative geometry. I will tell you why. Like for example, quantum mechanics, you have classical mechanics which we know from Newton's thing. There is a h bar, Planck's constant. If you take the Planck's constant going to zero in some hand-waving way in many places, you will get the classical results. The quantum mechanics produces many times classical results. There are still problems. We have to be very careful about it. It's a subtle limit. Similarly, the non-commutative geometry, in the limit of the Planck constant, the Planck length goes to zero, it will become what we call as a Riemannian geometry. So some examples. So we know in quantum mechanics we use an operator x and another operator called momentum p, which is essentially d by dx, acting on functions, wave functions. They have a relation x with p, commutator is I h bar. So replace it by x1 with x2 is I theta. That's what is the thing. So phase space in classical mechanics, which is x and p, is no longer commutative. You are not considering functions of x and p. Another function x and p commute. They are numbers in classical mechanics, but no longer true because they are operators. So similarly, you have to introduce such a thing, and one such, this is a toy model example. There is a name for it which is called Moyal model or Moyal space. Now this kind of a thing can experimentally be happening in some experimental situation like quantum Hall effect. Now there is another example which is known as the sphere. Sphere is x1 square plus x2 square plus x3 square is equal to r square, right? That is what is a sphere, right? Regular round sphere. But you are assuming x1, x2, x3 are commuting. If you assume they don't commute, but they obey that equation 8, okay, they don't, x1, x2 commutator is I times x3. If you do that, then it becomes a different thing. You have to start describing the space, sphere, by quantum mechanics of angular momentum. Angular momentum. This we have been doing for the past 80 years or something like that, and that is what you have to use. But unfortunately, this kind of geometry which I talk about is toy models. What is nature? Do we know what is there in nature? Standard model which we know, can it produce that? We don't have a guiding principle for that. So there is a set of work by Alan Kohn and others, and they are very interesting. They introduce something interesting. So let's go back to the Gij, dxi, dxj, where dxi, dxj are translation. You go from one point to another point, which is what we call as the momentum of d by dx will tell you how to go from one point to another point, derivative of the function. So the dx and dx, which I wrote, you even put a dt there. Dx by dt will make it square of velocity, which is what we call as the kinetic energy of mv square. That mass term which is there, which is multiplying, is played by the Gij, which can be taken as Gij. The metrical information is mass of mv square, that Gij is there. So this is what is played by the ds term. Okay? So instead of that, he introduced this term, cone, which is called Dirac operator, which is what I wrote earlier, gamma mu d mu. The d mu is your kinetic energy kind of piece, and that gamma mu is connected with g mu nu, which is gamma nu anticommutator is g mu nu. The metrical information, the local information is carried by that gamma matrices, which is Clifford algebra. So he created a new structure which is called spectral table. Instead of space-time, which is commutative space of functions, he introduced space of functions or some algebra which is not commutative. That algebra is what I have written as curly A. And it replaces the space-time. And H is the Hilbert space on which these functions, the algebra is realized. And D is the Dirac operator. So this will tell you what is the geometry which we want to have. If I can create a good algebra, if I can create that Hilbert space, if I can make correct meaning of the Dirac operator, then all my set that I have replaced what was done by Riemann, what was done by Einstein, to a quantum geometry, But the question remains, what is the algebra? We don't know. But whatever algebra you have, you should get back to at least in some scale, like LP going to 0 kind of limit. We should get our standard model. We should get our general relativity. We should get back what we know. The same question was there in quantum mechanics. Whatever quantum mechanics of particles at atomic scale is there, we should understand why if I throw a stone, it follows the Newton's law of motion, right? At that scale of physics. So that kind of a thing has to be obtained. Such a thing was done, which is called almost commutative space. It is non-commutative, but almost commutative. So that if you make that almost go to 0, you will get back your old thing. And that algebra which was required was space of functions on R4, that Minkowski space-time, followed by a 2 by 2 matrices, which is called the Quaternion Matrix, which quaternions were created by Hamilton, and incidentally today was the birthday of Hamilton, and another one which is the complex matrices, 4 by 4 matrices. So this is like extra dimensions. So you have the space of functions, and then you have space of matrices, a thing which tells you what is the algebra. It's a direct product of these two things. And this is something like Kalusak line, which I told you, you put an extra circle, right, extra sphere in 4 dimension at every point, which is very tiny that you don't perceive it. That kind of a thing, and this is called almost commutative geometries. And this way they could get the standard model. Can they get anything beyond? Answer is unfortunately no. They are unable to predict something more that will give them a guideline for experimentally where you are looking for. This is what is the thing. So this is basically the way in which the whole thing was done. And I will not explain Dirac operator, which is here, which was written for another place. So this is the direct product there is, the first part is for the algebra of functions in Minkowski space. The second part is for the internal space. You can call it internal space. So the way to compute is also given by them, and they can actually produce standard model in some corrections, and they claim some success in understanding. Still it is understanding what is happening in standard model. They hope that it will help in going beyond where quantum space-time will be used. Okay. Now there are other things also which was done in 70s, which is very interesting. Now I told you about quaternions. Quaternions are only what Pauli matrices are introduced, sigma 1, sigma 2, sigma 3. That is it. Yeah, what they were asking is the question, you have an equation x square is equal to minus 1. What x is equal to plus or minus I. So they introduced that I, complex numbers were introduced. Now you can ask the question, can I have more than one of that type? So they introduce, for example, sigma 1 square, sigma 2 square, sigma 3 square, essentially 2 by 2 matrices. A matrix A square is equal to minus 1. How many solutions are possible for that? 2 by 2 matrix. And that is what that quaternionic algebra is. There is nothing more than that. It's a 2 by 2 matrix, A square is equal to minus 1. Find the solutions of that. That's all. Okay? The space of such solutions is what quaternionic algebra. Now the next thing is, can I go beyond that? And such a thing was created in 70s, well known earlier by maths people, which is called octonionic algebra. These are all what are known as division algebras. There is, if you have a non-zero element, two of them, A and B, if you multiply, it will be always non-zero. If one of them is 0, the answer will be 0. That's what x, y is equal to 0 means, x is 0 or y is 0. That's a kind of a thing happening even for matrices. This is what division algebra is. And the octonic algebra was created, and they are very interesting. And for example, you can produce the same standard model which is there with 3 families, family structure also, using this algebra. It was done in 70s. Now people think they may be useful in going to that extra space using those algebras. And very interestingly, but I will not go into that. So we realize the need for geometry beyond Riemann. The need arises from the description of space-time within the framework of quantum theory. You need space-time also is a quantum object. Quantum mechanics has to be obeyed by it. And that essentially was stated without using the word quanta. He stated more or less the same thing, Riemann himself. The question of validity of the hypothesis in the infinitely small is connected with the question of all these things which I have made. So he asked the question, I have to measure that small distance. If I have to measure, I need a light ray. He called it light ray, light object, electromagnetic light. And that physics of that will start affecting that. He actually said that physics of light ray will change the distances by which you measure at the infinitesimal levels. This is what he said. Then he also asked this question, is space-time, which we all know, is it discrete or continuum? Right? Is it discrete? We find it to be completely continuum. Well, I find this chart also to be completely continuum. Right? But it is not. It's made up of lattice. Threads here and here. So you need equipments to measure, microscopes to measure this discreteness. So you need to go to that kind of length scales to measure. And that is a kind of a thing. The discreteness and this thing can also be questioned there. Now actually you can ask that question. And that is the most interesting thing which has been happening for the past 3 or 4 years at the level of quantum space-time. You can ask the question, can discreteness and continuum coexist? Can they be there together? Which it looks like in one way it's like a stupid question, but it looks like, is it possible? That kind of a thing. And the answer was given by sometime in 1930s by von Neumann and Jordan, who created quantum mechanics. Space-time before that was described by algebra of functions, which is commutative. But now space-time is described by not by algebra of functions. They are described by self-adjoint operators, operators which are Hermitian in what generic sense. Now these operators which tell you what is the space-time, they no longer commute. That's why non-commutativity also arises. Okay? But there is only one Hilbert space, which is called separable Hilbert space with a countable basis. But it has operators which have discrete spectrum as well as continuous spectrum. So you can have coexisting situation where continuum and discreteness be described in the same theory in a nice way. And that is possible only if you introduce quantum theory. So this new ingredient at the core of quantum calculus renders the framework of non-commutative geometry is effective. In such a Hilbert space, that's what von Neumann did, which happens, for example, we say that 1 particle, 2 particle, 3 particles Hilbert spaces. Now the quantum field theory talks about product of various Hilbert spaces, 1 particle, 2 particle Hilbert space, 3 particle. Now can I write it as product of that Hilbert space? Answer is it is not bipartite like that, because there is a symmetry group, there is identity and distinguishability of particles happen that you have to modulate, you have to divide it by a symmetry group, which is permutation group. So this is what was introduced by von Neumann in 1930s, which is called factorizations, which are not tensor product type H1 cross H2. There are three types. A friend will confirm whether I am saying correct or not. Sundar and Vijay, all these people are experts in this area. It's unfortunate, I have been talking to him various things about von Neumann algebra, I never asked him this question. So there are three types. One is a tensor product type, but not tensor product, but there is a trace. The third one is not either of this. Okay. Now there are some situations in type 3 where it can go to type 2 by some controlling parameters, and that is what is the thing. So quantum field theory, which we all talk about, swear by it till now, the operator algebra, which I have been asking for to describe space, time and particles together, they all come under type 3, and that is the most dangerous one. Okay, we don't understand completely. And how to handle this is one of the important questions, which in fact of late several papers are there. Okay, I have to conclude. Remove life from Einstein's beautiful theory by steamrollering first to flatness, because you want to make it flat and then put some corrections. Then we shall learn nothing from attempting to wave the magic of wand of quantum theory. If you want quantum theory, don't make it flat. Over the result. This is what Roger Penrose says. And it also introduces what is called the non-locality, which is there in quantum mechanics in one way of saying, and that's what he describes. So what we need, axioms that lie at the basis of quantum geometry, which will be beyond Riemann and beyond Einstein. So I have some references. The most interesting reference which I used extensively in this is a collection of papers from Riemann to Einstein, from that time to Einstein, and all these private diaries, etc., are also inside that. And it is so profound, by Riemann, some 3 or 4 of them, Helmholtz, and later by Clifford, Poincaré, some 2 or 3, various things where, in fact, number of equations in all these things is very limited. In all these things, it's almost like they're intuitive ideas they are talking about, and there are other people have done the work. I myself have done some work on this with Nikhil, which I mentioned about the dark matter question, and also about fuzzy geometries, and this is what I have to say, and I thank you, all of you. Hope I could make it nice.
So, thank you, Govindarajan, for that very thought-provoking lecture. Actually, there were so many thoughts already in this.
Yeah, talk. I hope nobody is going to throw stones at me. If I say ether is there within these definitions, people may be angry with me.
Any questions here? Yes,
Rahul.
No, since you also brought up ether again now, the Einstein's quote on ether from 20s was very interesting.
Yeah.
And he wanted to basically prove Mach's principle via general relativity, and he didn't succeed, right? But is there a link between that and?
Well, essentially he was influenced by Poincaré. Poincaré wanted to, or even Riemann himself, or those people in their private diaries which they have written, that there is some ponderable thing which has to be there. That's what their assumption. So you can even take general relativity, the current general relativity which is given by Einstein, go to the limit velocity of light goes to infinity. That's a contraction which people do. Then what you have is Newtonian gravity, but the three-dimensional space in that Newtonian gravity is curved, because this was originally you started with the curved space and that goes into the curvature. That's the kind of thing Poincaré was talking about. So the three-dimensional space is curved, that's why there are geodesics in that curved space, and even light bends there, So that was actually forcing Einstein to think more, and then this idea that ether kind of medium is there, but what he made the remark is, we cannot call it by a regular matter, regular elastic properties matter. In fact, around the same time with Bose's paper in 1924 or 5, where he wrote about the famous statistics, Bose statistics. There was a big talk about it, and he was very impressed with that because it gelled with what he wanted, and he used immediately to produce a Bose-Einstein gas. For the kinetic theory of gases, he just put it, that's all. Statistics, he put it. Free Bose gas. No interaction, they are not interacting at all. And then they found that there is a new phase of matter. That phase of matter is Bose-Einstein condensate. So that kind of matter, he himself was not able to put it even in general relativity. Possibility is there, that is what one is thinking along. So it is likely that these things were bothering him in a big way. That's why his ideas of quantum mechanics and entanglement, because if you are having a Bose-Einstein condensate, it's a completely state is created by all the particles together. They are entangled in some sense. The wave function is wave function of all the particles together. Okay, you cannot say that this is the wave function of this particle. So that is a kind of a problem. So these things were bothering him from 1920s to 40s. He was not completely successful, but his thoughts are very interesting. That's what I wanted to say.
Hello. So can you please show the curve that distance versus velocity curve while explaining dark matter is showed?
Yeah.
Yes. So the first question is a distance with respect to what?
From the center of the galaxy. Like Milky Way, there is a Sagittarius, this thing. From there, actually, very interestingly, there are stars very close to that thing. You don't see it because it's a black hole. But what you see is there are stars around that going in elliptical orbit like our Keplerian orbit. From the motion of those stars, they even guess the mass, what is there, which is making them going in Keplerian orbit. And that gives you something like million solar masses for that. If there is an object like that, it has to have million solar masses. We don't see it. Now from that central point, you can look at distant stars, etc., various things. And the similar thing can be done for other galaxies also. Now they have thousands of galaxies have been analyzed.
You can also do it for galaxy clusters.
Clusters also, which I wrote.
In the galaxy clusters, the galaxies themselves move in such a way that they reproduce these rotations.
That's also there. Not only for galaxy, even galaxy cluster is collection of galaxies.
So another question is that you said from Newton's law, from Kepler's law, we expect the velocity to go down with respect to distance.
No.
But in this graph, we see the velocity is also going up for the B curve.
Right.
Why is that?
This one.
Yes,
No, see, the point is there is, even in sun, when the thing is there, even by several stars in that, there is some speed due to the contribution by other stars. In the neighborhood of that, speed will increase. So there is some distribution of the matter itself which is affecting. But beyond that, there is something else which is dark matter, which is starting beyond a distance. See, there is a galaxy and there are several stars.
Okay.
You can talk about the density up to
Yes,
the core.
yes.
You can talk about the core.
Yes.
The core is what is I'm talking.
Okay. I was thinking about planetary motion. So here
We don't have a core except for the sun. There is only sun.
Yes.
But for the galaxy, there is some core of stars
So
also.
planets are moving inside the core also, and there the velocity is.
That's
Thank you.
Hello. Yes, sir. Thanks for a very interesting talk. So I was wondering what geometric formulation for von Neumann algebra for type 3?
No, we don't have. So what they look for, I can only tell you the current guesses. They are looking at quantum field theories. Instead of Minkowski space-time, if you go to de Sitter space, then it becomes type 2, the converts itself. Some kind of arguments are there. We don't have a good understanding of those von Neumann algebras which are relevant for describing quantum space-time as of now. It may become better, we don't know.
quantum many-body states, can I define the geometry, like can I define the distance between them, geodesic distance between them on the state manifold? Is it possible?
Well, we have to define not between 2 points, we have to define distance between 2 states.
Right.
That is the kind of, that people do even in the Hilbert space, what is the distance between 2 states, etc. How the evolution will take place from one state to another state. That kind of principle can be done. That is true. There is no unique metric where that control is there. So that's why that formulation in terms of what is called trace formula, which was used by Feynman to describe only physics. He is not worried about the thing. May be useful as a explaining nature. That is what is it. It may not solve all the Hilbert space problems. Yeah. Subhashri also wanted to ask. Okay.
Since we are on, I have 2 questions. One is on that curve. Is there a amount of scale of coarse graining involved in both curve A and B? Like, what is the error order which you would ignore?
I'm not the expert to answer this, but I will make my effort. There is definitely a coarse graining because the stars are now considered as molecules of this thing. That's the kind of thing. And the scale which I'm talking about is very large. So in that, we can ignore all that and go to this part.
Is it of the order of light years or is it less
No,
than?
it's of the order of parsecs and hundreds of parsecs of our Milky Way. Since you asked this question, there are galaxies where, like Milky Way, there are millions of stars are there. Okay, millions of stars are there. But there are galaxies which are called dwarf galaxies. And the dwarf galaxies will have 1,000 stars, 500 stars, not big. Okay, their distance is of the order of what people call as the parsec. It's 3 light years, approximately 3 light years is 1 parsec. It's about 1,000 light years. Whereas here in Milky Way, we are talking about millions of light years away. So here it is 1,000, and such galaxies are also there. And dark matter is seen there also. Dark matter is seen there also, and they can draw the profile of the dark matter density. That also is there. And those densities which drawn by this thing, they agree very well with the kind of model which I was trying to try as the ultra-light dark matter. The other things have some problem because they try to blow up at the center, but doesn't happen in these models. That's the advantage of this.
Can I?
There.
Okay, sure.
Yeah, I can hear you. Don't thank. Go ahead. Okay, so the scale is, these are all isolated gravitational waves, the 2 black holes or black hole and neutron star collapsing together and produce a violent event, and that happens several million years before happened, and it is coming to us. So when they say gravitational wave and light wave have the same speed, what they mean is it happened several million light years before. The light has been traveling, as well as the gravitational wave, both are traveling from that time when it happened. We can more or less, with the optical thing, we can, when they see this thing, they can ask those telescope people to go and look at that direction. And they do find it. Some of them, they do find it. So now they can compute how long does it take for the light to come, how long does it take for the gravitational wave to come. And those 2 things agree to the reasonable experimental thing, that the velocities are same. There will be experimental accuracies for that. That is the first part of the thing, at the microsecond level, etc. That is what will happen. They are very beautiful things. So these are all not like dark matter or dark energy question where large number of things are involved. Isolate. So sun and earth, general relativity works very well. Even Newtonian theory works very well. the stars close to Milky Way, the center, general relativity works very well, no problem. But general relativity doesn't work when it considers large number of stars inside the Milky Way galaxy, where large number of particles, the stars are there, millions. We don't know. Okay, that is the problem. Yes.
Hello. Hi, sir. So you said you talked about this ultra light dark matter, and you said that it created in early universe and it travels with the speed of light.
Almost, if it is there, it will travel at the thing, but they form this condensate. If the condensate together cannot travel at the speed of light, that's a problem.
Yeah, so
that
is what I'm not able to correlate, like it travels near to the speed of light.
If it is left alone, it will travel. Like neutrino, if it is left alone, it will go at that speed. But neutrino inside some very heavy density, this like for example, even inside the sun to come, they travel less than the speed of what you would expect. So what it travels speed at vacuum, what it happens in medium is different.
So but most of the space is empty, right? Like
that's what is the question. These particles themselves, okay, like the thing, they form what is called fluid, very large number of them, and that will be the background medium, what people may call it as ether or whatever it is. So that's the problem.
So Bose-Einstein conditions happening only at the place where large visible matter there, that's what?
No, these are all visible, but not visible. No, why should it be invisible? Bose particles, obeying Bose statistics, is enough to form the condensate. Is enough to form. In fact, that's what Einstein did for Bose-Einstein condensate, was he was taking free particles. Kinetic theory of gases, which we do in colleges. Instead of, he also said they obey quantum mechanics. Second, they have identical and indistinguishable. That's all he used. What Bose gave, he essentially used it. But Bose gave it for photons, but are supposed to be without mass. Now these are all particles which have some mass. That's all.
But this happens at some temperature, right?
The temperature is, so if it is very, very, very low mass, like 10 to the power minus 22 electron volt, the critical temperature below which the condensate will be formed will be 10 to the power 18 degrees centigrade.
Very early universe.
Very early universe. It will be formed. Like the condensate which we see in the lab, it is formed if the temperature is less than nanokelvin. Okay? Very small. But that is because the gas which they took here was using rubidium. Rubidium nucleus has about 100 GeV or 100 into 10 power 9 electron volt. Whereas the particle which I am talking about has 10 power minus 22 electron volt. Just see the order of magnitude difference. That's what makes a difference.
Yeah, one last question. Why are you calling it as a ether or ether-like medium?
Well, that's only a name. There is some fluid of these things can be talked about only as a fluid, or we can't talk about individual particles, right? The meaning of individual particles is lost in such situation. So we have to talk in terms of a fluid. Like for example, water in a tube, okay, flowing. We don't talk about the H2O there, molecules, right? They're all collectively going together. So it's like a fluid which collectively exists at that thing. That's what is there.
Yeah, just one more thing. So is it like a classical field more?
It's only for visualization, I'm telling, because Bose-Einstein condensate has to be visualized in that framework.
But
it's like a superfluid.
So I think before we go, I have one question. So when you are talking about this Bose condensation of these very, very light particles, it has to be compared with this cold dark matter, where the dark matter particles are much heavier than proton or neutron, as we know. That comes from the fact that one, there is a large scale structure of the universe which you can explain the distribution of the visible matter by the distribution of the dark matter particles exerting gravitation. And the second very important evidence for that cold dark matter is the fluctuations in the cosmic microwave background radiation, the power spectrum. Now those two are very well explained by cold dark matter, which is very heavy. So you are talking about extremely light. So at least before condensation, it is very warm dark matter. So it cannot give rise to large scale structure formation.
Okay.
But if you are claiming that they are condensates, then you should also be able to explain, using the condensate idea, the large scale structure.
Yes. So,
Can you?
Okay. So at the moment, there are several models for the dark matter, and we are not in a situation one is better than the other. There are a lot of problems in one, in some places, etc., and all these things are the thing. The structure formation itself, so the whole question, since I talk about close to the Big Bang, these things are formed, when I say maybe million years after this thing.
Big Bang.
So Big Bang. So now is the time how the galaxies were formed. That's a question Webb is asking. How the initial stars are formed. How do they collect together and form? So we are not in a situation to answer the kind of questions you are saying till the results from all these 300 light years after the Big Bang. That's what Webb is going to do. Okay, 300 million years after that. When the first stars were formed, what that 21 centimeter kind of experiment, this thing we look for, how they accumulate to form a galaxy, etc. Those structure formations can be understood, and preference for one dark matter over other dark matters will happen at that level, to a better thing. At the moment, we cannot say that, beyond that.
I have a question. There was a point in the slide that space-time are the operator in the Hilbert space. So in the classical limit, we have to define the distance. So how we are going to define the distance between the operator? And second question is that can we think of all whole universe as a one single Hilbert space, and anything we do?
Okay. So mathematically, he will probably confirm there is only one separable Hilbert space. Okay, and there are subspaces where operators, etc. are there. Now, there are parameters like h bar, which play a role in some sense of group theoretic or thing, which are fundamental, like fine structure constant, etc. We can think in terms of, if I want to understand classical mechanics, can I go from quantum mechanics to classical mechanics by the parameter going to 0? In regular quantum mechanics classes, we will teach that thing as some Ehrenfest theorem, where you take expectation values and then whether they go to the thing. Or even in harmonic oscillator, we take coherent states, and they have a behavior which is close to that. So in that sense, we should be able to talk about these things also. So the limit of parameters going to this thing is your commutative algebra, but the real universe, real physics, or real nature is quantum. We cannot avoid it. Okay? So we can think in terms of what is the approximate sense in which, in some scales, we can talk about. And that will be what we expect from common sense. But what we expect from common sense can be different at different scales. What happens inside? If you take an electron and drop it, is it going to do what a stone is going to do? No, it will not do that. That's a problem. Okay, that's the difference, because the mechanics of an electron dropped here and a stone dropped here could be entirely different descriptions. We cannot compare them.
Okay, so if there are no more questions, let us thank Professor Govindarajan for a very thought-provoking lecture.
Yes.
And thank you all for very provocative questions too.
Thank you very much. I enjoyed. Thank you.